Chapter 11, Managing Systems Implementation. We've been through the planning phase, we've done systems analysis, we've designed our system, and now it's time to implement. Managing systems implementation involves application development, testing, documentation, training, data conversion, system changeover, and post-implementation evaluation of the results. We'll cover each of these during the course of this chapter. Throughout systems implementation, the system design specification serves as the blueprint for constructing the new system. The initial task is application development. This requires the systems analysts and the programmers to work together to construct the necessary programs and to code the modules. Before a changeover, the system has to be tested and documented carefully. Users have to be trained and the existing data must be converted. After a new system is operational, then a formal evaluation of the results takes place and becomes a part of a final report to management. Application development is the process of constructing the programs and code modules that will serve as the building blocks of the information system. At this point, we're going to stop and review the tasks that were involved in the creation of the system design. In Chapter 4, we talked about requirements modeling and how to use functional decomposition diagrams to break complex business operations down into smaller units or functions. In Chapter 5, we learned about structured data and process modeling, and we created data flow diagrams. We also developed process descriptions for functional primitive processes that documented the business logic and the processing requirements. In Chapter 7, we selected our development strategy. In Chapter 8, we talked about the user interface and how it should be designed. In Chapter 9, we worked with the data design issues. We analyzed the relationships between system entities and constructed entity relationship diagrams. And in Chapter 10, we considered an overall system architecture. Taken together, this set of tasks produced an overall design and a plan for the physical implementation. Building a new system requires careful planning. After an overall strategy is established, individual modules must be designed, coded, tested, and documented. A module consists of related program code organized into small units that are easy to understand and maintain. After the modules are developed and tested individually, more testing takes place, along with thorough documentation of the entire system. When you create program modules using a structured or an object-oriented method, you start by reviewing the documentation from the prior software development lifecycle phases and creating a set of program designs. If you built a documentation file early in the development process and updated it regularly, you now have a valuable repository of information. The centerpiece of your documentation is the system design specification, accompanied by diagrams, source documents, screen layouts, report designs, data dictionary entries, and user comments. If you used a case tool, which I would highly recommend, during the systems analysis and design process, your job now will be much easier. At this point, the coding and testing tasks actually begin. If you decided to use an agile approach, intense communication and collaboration will now begin between the IT team and the users or customers. The objective is to create the system through an iterative process of planning, designing, coding, and testing. Agile projects use various models, including the spiral model, which was shown in figure 1-30 on page 26 in our text, or the extreme programming example, which is shown in figure 11-7. Agile development and extreme programming are going to be discussed in detail later in this chapter. Each system development approach has its own set of tools that has worked well for that method. For example, structured development relies heavily on DFDs and structure charts. Agile methods tend to use spiral or other iterative models. System developers also can use multipurpose tools to help them translate the system logic into properly functioning program modules. These generic tools include entity relationship diagrams, flowcharts, pseudocode, decision tables, and decision trees. An ERD is a useful tool regardless of which methodology you're using, because the various relationships, one-to-one, one-to-many, and many-to-many, must be understood and implemented in the application development process. Flowcharts can be used to describe program logic and are very useful in visualizing a modular design. A flowchart represents logical rules and interaction graphically, using a series of symbols connected by arrows. Using flowcharts, programmers can break large systems into subsystems and modules that are easier to understand and decode. Pseudocode is a technique for representing program logic. Pseudocode is similar to structured English, which was explained in Chapter 5. Pseudocode is not language specific, so you can use it to describe a software module in plain English without requiring strict syntax rules. Using pseudocode, a systems analyst or programmer can describe program actions that can be implemented in any programming language. And finally, we have decision tables and decision trees. Decision tables and decision trees can be used to model business logic for an information system. In addition to being used as modeling tools, analysts and programmers can use decision tables and decision trees during systems implementation as they develop code modules that implement the logical rules. Regardless of whether structured analysis, object-oriented design, or agile methods are used, even a modest-sized project might have hundreds or even thousands of modules. For this reason, application development can become quite complex and difficult to manage. At this stage, project management is especially important. Users and managers are looking forward to the new system, and it's very important to set realistic schedules, meet project deadlines, control costs, and maintain quality. To achieve these goals, the systems analyst or project manager should use project management tools and techniques similar to those described in Chapter 3 to monitor and control the development effort. Structured application development usually involves a top-down approach, which proceeds from a general design to a detailed structure. After a systems analyst documents the system's requirement, he or she breaks the system down into subsystems and modules in a process called partitioning. This approach is also called modular design, and it is similar to constructing a leveled set of DFDs. By assigning modules to different programmers, several development areas can proceed at the same time. Because all the modules have to work together properly, an analyst must proceed carefully with constant input from programmers and IT management to achieve a sound, well-integrated structure. The analyst also must ensure that integration capability is built into each design and thoroughly tested. Structure charts show the program modules and the relationships among them. A structure chart consists of rectangles that represent the program modules, with arrows and other symbols that provide additional information. Typically, a higher level module called a control module directs lower level modules called subordinate modules. In a structure chart, symbols represent various actions or conditions. Structure chart symbols represent modules, data couples, control couples, conditions, and loops. A rectangle represents a module as shown in the figure at left. Vertical lines at the edges of a rectangle indicate that module 1.3 is a library module. A library module is reusable code and can be invoked from more than one point in the chart. An arrow with an empty circle represents a data couple. A data couple shows that one module passes to another. An arrow with a filled circle represents a control couple. A control couple shows that a message, also called a status flag, which one module sends to another. A module uses a flag to signal a specific condition or action to another module. A line with a diamond on one end represents a condition. A condition line indicates that a control module determines which subordinate modules will be invoked, depending on the specific condition. A curved arrow represents a loop. A loop indicates that one or more modules are repeated. Cohesion and coupling are important tools for evaluating the overall design. It's desirable to have modules that are highly cohesive and loosely coupled. Cohesion measures a module's scope and processing characteristics. A module that performs a single function or task has a high degree of cohesion, which is desirable. Because it focuses on a single task, a cohesive module is much easier to code and to reuse. If a module must perform multiple tasks, more complex coding is required, and the module will be more difficult to create and to maintain. If you need to make a module more cohesive, you can split it into separate units, each with a single function. Coupling describes the degree of interdependence among modules. Modules that are independent are loosely coupled, which is desirable. Loosely coupled modules are easier to maintain and modify because the logic in one module does not affect other modules. If a programmer needs to update a loosely coupled module, he or she can accomplish that task in a single location. But if modules are tightly coupled, one module is linked to the internal logic contained in another module. It would be preferable to have modules that are loosely coupled and logically independent. Typically, you follow 4 steps when you create a structure chart. You review DFDs to identify the processes and methods, identify the program modules and determine control subordinate relationships, add symbols for couples and loops, and analyze the structure chart to ensure that it's consistent with your system documentation. Your first step is to review all DFDs for accuracy and completeness, especially if changes have occurred since the system's analysis phase. A method is similar to a functional primitive, and it requires code to implement the necessary actions. Working from the logical model, your next step is to transform functional primitives into program modules. When analyzing a set of DFDs, remember, each DFD level represents a processing level. If you're using DFDs, you would work your way down from the context diagram to the lower level diagrams, identifying control modules and subordinate modules, until you reach functional primitives. If more cohesion is desired, you can actually divide processes into smaller modules that handle a single task. Next, you add the couples, loops, and conditions to the structure chart. If you are working with DFDs, you can review the data flows and the data dictionary to identify the data elements that pass from one module to another. In addition to adding couples, you add control couples where a module is sending a control parameter or flag to another module. You also add loops and condition lines that indicate repetitive or alternative processing steps. And finally, at this point, the structure chart is ready for careful analysis. You should check each process, data element, or object method to ensure that the chart reflects all previous documentation and that the logic is correct. You should also determine that the modules are strongly cohesive and loosely coupled. Often, you have to draw several versions of the chart. Some case tools can help you analyze the chart and identify any problem areas. Agile development is a distinctly different systems development method. It shares many of the steps found in the traditional development, but it uses what we call a highly iterative process. The development team is in constant communication with the primary user, who's called the customer, shaping and forming the system to match the customer's specifications. Agile development is aptly named because it's based on a quick and nimble development process that easily adapts to change. Agile development focuses on small teams, intense communication, and rapid development of iterations. We also learned in Chapter 1 about extreme programming, which is one of the newest Agile methods. Extreme programming is an iterative approach. where a team of users and developers immerse themselves in a systems development. XP supporters emphasize values such as simplicity, communication, feedback, respect, and courage. Success requires a strong commitment to the process, corporate support, and dedicated team members. In extreme programming, the customer begins by meeting with the programmers and providing user stories. A user story is a short, simple requirements definition. Programmers use user stories to determine the project's requirements, priorities, and scope. User stories do not deal with technical details, and they're short and they're often written on index cards. Each user story is given a priority by the customer so the requirements can be ranked. Programmers assign a score to each story that indicates the estimated difficulty of implementation. Projects are often composed of many user stories from which programmers can estimate the scope, time requirements, and difficulty of the project. In addition to user stories, frequent face-to-face meetings with customers provide a higher level of detail as the project progresses. The team must also develop a release plan which specifies when user stories will be implemented and the timing of releases. User stories are implemented in a series of iteration cycles. An iteration cycle includes planning, designing, coding, and testing of one or more features based on the user stories. At the beginning of each iteration cycle, which is often 2 weeks long, the team holds an iteration planning meeting to break down the user stories into specific tasks that are assigned to team members. Extreme programming uses an interesting concept called parallel programming. In parallel programming, two programmers work on the same task on the same computer. One drives, or programs, while the other navigates, watches. The onlooker examines the code strategically to see the forest, while the driver is concerned with the individual trees immediately in front of him. The two discuss their ideas continuously throughout the process. Another important concept of extreme programming is that unit tests are designed before the code is written. This test-driven design focuses on end results from the beginning and prevents programmers from straying from their goals. Because of the magnitude and intensity of the multi-cycle process, agile testing relies heavily on automated testing methods and software. Agile methodology is becoming very popular for software projects. Its supporters boast that it speeds up software development and delivers precisely what the customer wants, when the customer wants it, while fostering teamwork and empowering employees. However, there are drawbacks to this adaptive rather than predictive method. Critics of agile development often claim that because it focuses on quick iterations and fast releases, it lacks discipline and produces systems of questionable quality. In addition, agile methodology may not work as well for larger products because of their complexity and the lack of focus on a well-defined end product. Before implementing agile development, the proposed system and development methods should be examined carefully. As experienced IT professionals know, a one-size solution does not fit all. Coding is the process of turning program logic into specific instructions that the computer system can execute. Working from a specific design, a programmer uses a programming language to transform program logic into code statements. Each IT department has its own programming environment and standards. Visual Basic, Python, Ruby, and SQL are examples of commonly used programming languages, and many commercial packages use a proprietary set of commands. To simplify the integration of system components and reduce code development time, many programmers use an integrated development environment, or IDE. IDEs can make it easier to program interactive software products by providing built-in tools and advanced features such as real-time error detection, syntax hints, highlighted code, class browsers, and version control. As we learned in Chapter 7, IBM WebSphere and Microsoft.NET are popular IDEs. We also learned in earlier chapters that systems analysts use application generators, report writers, screen generators, and fourth-generation languages along with other case tools that produce code directly from program design specifications. Some commercial applications can even generate editable program code directly from macros, keystrokes, or mouse actions. Testing the system is a critical part of any software development project. System testing consists of three parts: unit testing, integration testing, and system testing. The testing of an individual program or module is called unit testing. The objective here is to identify and eliminate execution errors that could cause the program to terminate abnormally, and logic errors that could have been missed during desk checking. And as you read in the text, desk checking is the process of reviewing the program code to spot logic errors which would produce incorrect results. The testing of two or more programs that depend on each other is called integration testing or link testing. For example, consider an information system with a program that checks and validates customer credit status and a separate program that updates data in the customer master file. The output from the validation program becomes input to the master file update program. Testing the programs independently doesn't guarantee that the data will be passed between them correctly. Only by performing integration testing for this pair of programs can you make certain that the programs will work together properly. After you complete your integration testing, you have to perform system testing. This involves the entire information system. A system test includes all typical processing situations, and it's intended to assure users, developers, and managers that the program meets all specifications and that all the necessary features have been included. Regardless of how the system was developed, system testing has the following major objectives: perform a final test of all programs, verify that the system will handle all input data properly, both valid and invalid, ensure that the IT staff has the documentation and instructions needed to operate the system properly, and that backup and restart capabilities of the system are adequate. The details of creating this sort of documentation we're going to talk about in just a little while. Demonstrate that the users can interact with the system successfully. Verify all systems components are integrated properly and that the actual processing situations will be handled correctly. Confirm that the information system can handle the predicted volumes of testing in a timely and efficient manner. Successful completion of system testing is the key to user and management approval, which is why system tests are called acceptance tests. Final acceptance tests, however, are performed during the system's installation and evaluation. Documentation describes an information system and helps the users, managers, and the IT staff who have to interact with it. Accurate documentation can reduce system downtime, cut costs, and speed up maintenance tasks. Documentation includes program documentation, system documentation, operations documentation, and user documentation. Program documentation describes the inputs, outputs, and processing logic for all program modules. The program documentation process starts in the systems analysis phase and continues during systems implementations. Systems analysts prepare overall documentation such as process descriptions and report layouts early in the software development lifecycle. This documentation guides programmers who construct models that are well supported by internal and external comments and descriptions that can be understood and maintained easily. System documentation describes the system's functions and how they're implemented. System documentation includes data dictionaries, data flow diagrams, object models, screen layouts, source documents, and the system's request that initiated the project. Systems documentation is a necessary reference material for the programmers and the analysts who have to support and maintain the systems. Operations documentation contains all the information needed for processing and distributing online and printed output. Finally, user documentation consists of instructions and information to users who will interact with the system and includes user manuals, help screens, tutorials. Programmers or systems analysts usually create documentation and systems documentation, that is, program documentation and systems documentation. Systems analysts usually are also responsible for preparing documentation to help the end users learn the system. Uh, Most users prefer online documentation, which provides immediate help when they have questions or encounter problems. Although online documentation is essential, written documentation material is also valuable, especially during user training and also for reference purposes. After systems testing is complete, you present the results to management. You should describe the test results, update the status of all required documentation, and summarize the input from users who participated in the system's testing. You also must provide detailed time schedules, cost estimates, and staffing requirements for making the system fully operational. If system testing produced no technical, economical, or operational problems, management determines a schedule for system installation and evaluation. The new system is now ready to go to work. Your earlier design activities produced the overall architecture and processing strategy, and you consulted users at every stage of development. You developed and tested programs individually, in groups, and as a complete system. You prepared the necessary documentation and checked it for accuracy, including support material for IT staff and users. Now you will carry out the remaining steps in system implementation. These are to prepare a separate operational and test environment, provide training for users, managers, and IT staff, perform data conversion and system changeover, carry out a post-implementation evaluation of the system, and present a final report to management. No system can be successful without proper training, whether it involves software, hardware, or manufacturing. A successful implementation system requires training for users, managers, and IT staff members. The entire systems development effort can depend on whether or not people understand the system and know how to use it effectively. You should start to consider a training plan early in the systems development process. As you create documentation, you should think about how to use that material in future training sessions. When you implement the system, it's essential to provide the right training for the right people at the right time. The first step is to identify who should receive training and what training is needed. A manager, for example, does not need to understand every submenu or feature, but he or she does need a system overview to ensure that users are being trained properly and are using the system correctly. Similarly, users need to know how to perform their day-to-day functions, but they don't need to know how the company allocates system operational charges among user departments. IT staff probably need the most information. To support the new system, they have to have a clear understanding of how the system functions, how it supports business requirements, and the skills that users need to operate the system and perform their tasks. After you identify the objectives, you must determine how the company will provide training. The main choices to obtain training is to obtain training from vendors, outside training firms, or use the IT staff and other in-house resources. If the system includes the purchase of software or hardware, then vendor-supplied training is one of the features you should include in your RFP, your request for proposal. Many hardware and software vendors offer training programs fee-free or at a nominal cost for the products they sell. The training usually is conducted at the vendor's site by experienced trainers who provide valuable hands-on experience. If a large number of people need to be trained, you might be able to arrange classes at your location. Vendor training often gives the best return on your training dollars because it's focused on the products that vendor sells. The scope of vendor training, however, usually is limited to a standard version of the vendor's software or hardware. You might have to supplement that training in-house, especially if your IT staff customize the package. Many vendors offer web-based training options, including webinars, podcasts, and tutorials. A webinar, which combines the words web and seminar, is an internet-based training session that provides an interactive experience. Most webinars are scheduled events with a group of pre-registered users and an online presenter or instructor. A pre-recorded webinar session can also be delivered as a webcast, which is a one-way transmission whenever or wherever the user wants or needs the training support. A podcast refers to a web-based broadcast that allows a user to download local multimedia files to a PC or portable device. Podcasts can be pre-scheduled, made available on demand, or delivered as automatic updates depending on the user's preference. An advantage of a podcast is that subscribers can access the recorded material anywhere, anytime. And finally, a tutorial is a series of online interactive lessons that present material and provide a dialogue with users. Tutorials can be developed by software vendors or by a company's IT team. A tutorial example is included in the in-house training section of your text. You can also look into an independent training firm to provide in-house hardware or software training. If vendor training is not practical and your organization doesn't have the internal resources to perform the training, you might find that outside training consultants are a desirable alternative. If you decide to investigate outside training resources, you can contact a training provider and obtain references from clients. You could also seek assistance from nonprofit sources with an interest in training, including universities, industry associations, and information management organizations. When developing a training program, you should keep the following guidelines in mind. First, train people in groups with separate training programs for distinct groups. If the group is small, the trainees can learn from the questions and problems of the other people in the group. A training program must address the job interests and skills of a wide range of participants. Next, select the most effective place to conduct the training. Training employees at your company's location offers several advantages. Employees incur no travel expense, they can respond to local emergencies that require immediate attention, and training can take place in the actual environment where the system will operate. But you can also encounter some disadvantages. Employees who are distracted by telephone calls and other duties will not get the full benefit of the training. You also have to provide for learning by hearing, seeing, and doing. Some people learn best from lectures, discussions, and question and answer sessions. Others learn best from viewing demonstrations or from reading documentation or other material. Most people learn best from hands-on experience. You should provide training that supports each type of learning. And rely on your previous trainees. After one group of users has been trained, they can assist the others. Users often learn more quickly from coworkers who share common experiences and job responsibilities. Using a train-the-trainer strategy, you can select knowledgeable users who will then conduct training sessions for others. Usually, a relationship exists between training methods and costs. Training an airline pilot in a state-of-the-art simulator is quite different from helping corporate users learn a new inventory system. Obviously, training budgets are business decisions, and the IT staff sometimes has to work with the resources that are available rather than the resources they wish they had. Most people prefer hands-on training. However, other, less expensive methods can be used, including training manuals, printed handouts, and online materials. Regardless of the instructional method, training lessons should include step-by-step instructions for using the features of the information system. Training materials should resemble actual screens, and tasks should be typical of a user's daily work. The more realistic, the better. More sophisticated tutorials might offer interactive sessions where users can perform practice tasks and then view feedback. Video tutorials are extremely useful. You don't have to be a professional videographer to develop or create effective training tutorials. For example, the video learning sessions for this textbook were initially created as classroom teaching tools. Later, they were polished, edited, and transformed into streaming videos. Data conversion is a critical step in the process. I would caution you not to underestimate the time and difficulty that data conversion can present. During data conversion, existing data is loaded into the new system. Now, depending on the system, data conversion can be done before, during, or after the operational environment is complete. You should develop a data conversion plan as early as possible, and the conversion process should be tested when the test environment is developed. When a new system replaces an existing system, you should automate the data conversion process if it's possible. The old system might be capable of exporting data in an acceptable format for the new system or in a standard format such as ASCII2 or ODBC. ODBC, or Open Database Connectivity, is an industry standard protocol that allows database management systems from various vendors to interact and exchange data. Most database vendors provide ODBC drivers, which are a form of middleware. Now, if a standard format is not available, then you have to develop a program to extract the data and convert it into an acceptable format. Data conversion is much more difficult when the new system replaces a manual system, because all data must be entered manually unless it can be scanned. Even when you can automate data conversion, a new system often requires additional data items which might require manual entry. During data conversion, you should maintain strict input controls when the data is extremely vulnerable. You have to ensure that all system control measures are in place and operational to protect data from unauthorized access and to help prevent erroneous input. Even with careful data conversion and input controls, some errors are going to occur. For example, duplicate customer records or inconsistent part numbers might have been tolerated in the old system but will cause the new system to crash. Most organizations require that users verify all data, correct all errors, and supply every missing data item during conversion. Frequently, this process is called data cleansing. Although the process can be very time-consuming and expensive, it's essential that the new system be loaded with accurate, error-free data. System changeover is the process of putting the new information system online and retiring the old system. Changeover can be rapid or slow depending on the method. The 4 changeover methods shown on this slide are direct cutover, parallel operation, pilot operation, and phased operation. Direct cutover is similar to throwing the switch that instantly changes from the old system to the new. Parallel operation requires that both systems run simultaneously for a specified period of time and is also the slowest method. The other methods, pilot and phased operations, fall somewhere between direct cutover and parallel operation. We'll talk about these in the next few slides. The direct cutover approach causes the changeover from the old system to the new system to occur immediately when the new system becomes operational. Direct cutover is usually the least expensive changeover method because the IT group has to operate and maintain only one system at a time. Direct cutover, however, involves more risk than other changeover methods. If you're going to use a direct cutover method, you almost always want to have a fallback strategy. If the system should begin to fail, what will you do? What will you fall back to? Companies often choose the direct cutover method for implementing commercial software packages because they feel that commercial packages offer less risk of total system failure. And timing is very important when you're using a direct cutover strategy. Most systems operate on a weekly, monthly, quarterly, or yearly cycle. When a cyclical information system is implemented in the middle of any cycle, complete processing for the full cycle requires information from both the old and the new systems. To minimize the need to require information from 2 different systems, cyclical information systems usually are converted using the direct cutover method at the beginning of a quarter, calendar year, or fiscal year. The parallel changeover method requires that both the old and the new information systems operate fully for a specified period. Data is input into both systems, and output generated by the new system is compared with the equivalent output from the old system. When users, management, and the IT group are satisfied that the new system operates correctly, the old system is terminated. The most obvious advantage of parallel conversion is the lower risk. However, it does have some disadvantages. First, it's the most costly of all the changeover methods. Because the old and the new systems are in full operation, the company pays for both systems during the parallel period. Users have to work in both systems, which means dual entry, and the company might need temporary employees to handle that extra workload. In addition, running both systems might place a burden on the operating environment and cause processing delays. Parallel operation is not practical if the old and the new systems are incompatible technically, or if the operating environment cannot support both systems. The pilot operation changeover method involves implementing the complete new system at a selected location. The group that uses the new system first is called the pilot site. And during the pilot operation, the old system continues to operate for the whole organization, including the pilot site. If the system proves successful at the pilot site, it's then implemented in the rest of the organization, usually using the direct cutover method. Therefore, a pilot operation is really a combination of parallel operation and direct cutover methods. The phased operation changeover method allows you to implement the new system in stages or modules. One advantage of a phased approach is that the risk of errors or failures is limited to the implemented module only. Phased operation is less expensive than full parallel operation because you have to work with only one part of the system at a time. A phased approach, however, is not possible if the system cannot be separated into logical modules and segments. This illustration shows that each changeover method has risk and cost factors. As a systems analyst, you have to weigh the advantages and disadvantages of each method and recommend the best choice in a given situation. The final changeover decision will be based on input from the IT staff, users, and management, and the choice has to reflect the nature of the business and the degree of acceptable risk. A post-implementation evaluation assesses the overall quality of the information system. The evaluation verifies that the new system meets the specified requirements, complies with user objectives, and produces the anticipated benefits. In addition, by providing feedback to the development team, the evaluation helps improve IT department practices for future projects. A post-implementation evaluation should examine all aspects of the development effort and the end product, the developed information system. A typical evaluation includes feedback in many areas, and a checklist is included for you on page 547 in your text. You can apply the same fact-finding techniques in a post-implementation evaluation that you use to determine the system requirements during the systems analysis phase. Whenever possible, people who were not directly involved in developing the system should conduct the post-implementation evaluation. IT staff and users usually perform the evaluation, although some firms use an internal audit group or independent auditors to ensure the accuracy and completeness of the evaluation. When should a post-implementation evaluation occur? Is it better to wait until the new system has been in operation for a month or 6 months, a year or longer? Users can forget details of the developmental effort if too much time elapses before the evaluation. Ideally, conducting a post-implementation evaluation should be a standard practice for all information system projects. At the end of each software development lifecycle phase, you submitted a report to management, and the system's implementation phase is no exception. Your report should include final versions of all system documentation, planned modifications and enhancements to the system that have been identified, a recap of all the system's development costs and schedules, a comparison of actual costs and schedules to the original estimates, and post-implementation evaluation if it's been performed. The final report to management marks the end of the systems development work. In the next chapter, we'll study the role of a systems analyst during the systems operations, security, and support, which is the final phase of the software development lifecycle. To review, the systems implementation phase consists of application development, testing, installation, and evaluation of the new system. The analysts and technical writers also prepare operations documentation and users documentation. We talked about developing a training program, who needs to be trained, and what they need to learn and understand about the new system. And we talked about a post-implementation evaluation to assess and report on the quality of the new system and the work done by the project team. And as we just talked about, the final report to management included final system documentation. It described any future system enhancements that have already been identified, and it detailed the project costs. The report represents the end of the development effort and the beginning of the new system's operational life.